In this video, we will take a look at horizontal asymptotes and computational techniques for finding the limit as we approach infinity. In our last video, and you may have skipped over this part because I said to if you didn't really love the mathy definitions, but basically we talked about the official definition of a finite limit at infinity. And we said that we've got some line y equals L, and within epsilon units of each side, we could say once we pass some point M, all of the y values are going to be within epsilon units greater or less. So we could say that this line is y equals L minus epsilon, and this line would be y equals L plus epsilon. So again, not to get too mathy with it, but this line here in the middle, y equals L, that is the limit, but it's also the horizontal asymptote. So y equals L is the horizontal asymptote. Now, as we talked about in our last video, you can have 0 horizontal asymptotes, you could have 1 horizontal asymptote, or you could have 2 horizontal asymptotes. You can't have more than that because you can only have 2 if you had a different one going to the right and to the left. But the question is, and where we're going to spend most of our time in this video, is how do we find them? Let's begin by looking at rational functions that are in this form, c divided by x to the r, where c is just some constant and then x to the rth power. We can see from the two sample graphs, which are y equals 3 divided by x to the 5th and y equals 9 divided by x to the 6th, that either way it appears that I have a horizontal asymptote at y equals 0, and therefore the function has a limit of 0 as I approach infinity from infinity or negative infinity. But let's make sure this makes sense. So think about x equals 1 and x equals 10 in this first function. So if x equals 1 for this function, I get negative 1 and negative 10, because we're looking at negative infinity. I would have 3 divided by negative 1 to the 5th. So negative 1 5 times would be negative 1, and I would get negative 3. And I can even see on my graph that negative 1, negative 3 is a point on the graph. And then if I look at negative 10, that would be 3 divided by negative, and then 10 to the 5th power. So 1, 2, 3, 4, 5. So negative 100,000, which gives me negative 0.00003. And if I made x even larger, it would get even closer to 0 from the negative side. So it makes sense that, again, we can see that this is getting closer and closer to 0. And I could do the same thing for the second value, so x equals positive 1. This one's approaching positive infinity. And so I would have 9 divided by 1 to the 6th, which is 1. And then I would have 9 divided by 10 to the 6th, which is 1 with 6 zeros. And then that's obviously a very small number. And I could keep going and going and going. So it makes perfect sense that I would end up with a function that approaches 0, and therefore the horizontal asymptote is at 0. Real quick practice, what's the horizontal asymptote or asymptotes for f of x equals 5 minus 2 divided by x cubed? So again, I would find the limit as x approaches infinity of 5 minus 2 divided by x to the 3rd. Well, the limit of 5 is 5, and the limit of this is 0, because we just talked about the fact that that limit's always going to be 0. So in fact, you could write the limit as x approaches infinity of c divided by x to the r equals 0, and I could do the same thing for negative infinity. So what would I do here for negative infinity of 5 minus 2 divided by x to the 3rd? Well, this is 5 minus 0, so again 5. So this would have one horizontal asymptote at y equals 5. Feel free to graph that and verify that that is true. Let's make this a little tougher now. Now we want to find the limit and horizontal asymptote or asymptotes for another rational function, but it's not in the same form. So what a lot of students do, which is completely correct, would be let's find the limit as x approaches infinity of 2x minus 1 over x plus 1. And they would say, well, 2x minus 1 is going to be approaching infinity, and x plus 1 is going to approach infinity, and so it must be 1. Well, please don't do that. That's awful. This is called an indeterminate form, and we'll spend some more time on this. But for now, just know this isn't okay to have infinity over infinity. So we're going to use a technique to help us called the dividing out technique, basically. So I'm going to say the limit as x approaches infinity of 2x minus 1 divided by x plus 1 is equal to the limit. And what I'm going to do is I'm going to divide out the highest number of x's, or the highest degree of x's. And I'm going to take everything divided by that. So I'm going to take 2x divided by x. I'm going to take 1 divided by x. I'm going to take x divided by x, and I'm going to take 1 divided by x. So that means I have the limit as x approaches infinity. Let's just do some simplification. 2x divided by x gives me 2, and then 1 divided by x will stay 1 divided by x. X divided by x is 1, and then 1 divided by x will stay 1 divided by x. And now let's do the limit. The limit of 2 is 2. The limit of 1 divided by x is 0, because we just talked about that. The limit of 1 is 1, and the limit of 1 divided by x is 0, so I get 2 over 1, or 2. So that is, in fact, the limit. Now, I can do the same thing as I approach the left, but as we already know, I'm going to get all of this work is going to be exactly the same, and I'm still going to get 2. Why is it going to be the same? Because I have 1 divided by a very small number, a very large number, which makes the number very small and approaches 0. So in this case, I'm going to have just one asymptote, and that is at y equals 2. So again, we find the limit, but the asymptote is an equation of a line, y equals 2. I'd like you to press pause and try these 3 very similar questions first. Again, I'd like you to use the dividing out technique, and then we'll talk about some patterns that we see. So when you're ready, press play to see how you did. Again, for this first one, I'm going to take the limit as x approaches infinity, and I'm going to take everything divided by x squared, because that is, this is 2x divided by x squared, plus 5 divided by x squared. So I'm using x squared because squared is the highest degree. So 3x squared divided by x squared plus 1 divided by x squared. That's going to give me 2 divided by, I got to keep the limit in there. The first one, 2 divided by x plus 5 divided by x squared. And then this is 3 plus 1 divided by x squared. So what's the limit? The limit of 2 divided by x is 0. The limit of 5 divided by x squared is 0. The limit of 3 is 3, and the limit of 1 divided by x squared is 0. So I get 0 over 3, or just 0. So for my first one, I'm going to have a horizontal asymptote of y equals 0. So again, great job that you found the limit, but make sure you then write it as a horizontal asymptote. Next, let's look at the limit as x approaches infinity of 2x squared divided by x squared plus 5 divided by x squared divided by 3x squared divided by x squared plus 1 divided by x squared. So again, doing some cleanup. I'm getting limit happy here. Limit as x approaches infinity. This turns into 2 plus 5 divided by x squared, and then 3 plus 1 divided by x squared would give me 2/3, plus 0 plus 0. So we get 2/3, which means y equals 2/3 is my horizontal asymptote. Well, now let's look at that last one. If I take everything divided by x cubed, because that is, 2x cubed divided by x cubed, and I'm dividing by x cubed because it is the greatest power of x, and then 3x squared divided by x cubed plus 1 divided by x cubed. So we can see what's going to happen here is I'm going to get 2 plus 0 over, this is essentially 3 over x, which is 0 plus 0, which is undefined. So that means no horizontal asymptote. Now, what I do want to point out, now that we've done all of the hard work, is what we can see or what kind of patterns we might be able to pull from this. If I look at the first function, the degree on the bottom is greater than the degree on the top. And what's going to happen there is we're always going to end up with y equals 0, because looking at the most influential terms, this could sort of be looked at as the limit as x approaches infinity of 2x divided by 3x squared, which would reduce to 2 divided by 3x. So we're always going to have that power of x on the denominator that's greater, which is going to make this a very large number. So 2 divided by a very large number is 0. So if the degree on the bottom is greater, we're going to end up with y equals 0. If the degrees are the same, again, looking at the most influential term, this is like the limit as x approaches infinity of 2x squared over 3x squared, which reduces to just 2/3 by getting rid of the x squareds. And notice that's what we got over here. Looking at this one, if I reduced this, the limit as x approaches infinity of 2x cubed over 3x squared, if I reduced that, it's like 2x over 3. And so that is why I'm not going to have a horizontal asymptote, because this would be 2 times infinity divided by 3, which would be essentially infinity. But what I can tell you is, even though it doesn't have a horizontal asymptote, this actually has something called a slant asymptote. And I'm going to show you these graphs on the next page. So the slant asymptote is at y equals 2x over 3. And what's going to happen is, instead of some function like this, your function is going to follow along that slanted asymptote. Let's look at the graphs of those 3 functions just to verify what we found. When the degree in the numerator, the denominator is greater, we have y equals 0 as a horizontal asymptote. When the degrees are the same, we can reduce that fraction and we would have the line y equals 2/3 as a horizontal asymptote. And when the degree is greater in the numerator, we're going to end up with not a horizontal asymptote, but a slant asymptote at y equals 2x divided by 3. Let's take a look at a trickier example. And this one's tricky because, yes, it's a rational, which we understand, but we have the radical function within the rational function, which makes it a little trickier. Now, if I say the limit as x approaches infinity, the methodology that I used before was to divide by the greatest degree of x. And you might be saying, well, hold on, I see an x squared, but that's the square root of x squared, so really it's just x. So I'm going to take my radical function, and I'm dividing it by the square root of x squared. And so here, again, I've got the limit as x approaches infinity of 3 minus 2 divided by x. And in the denominator, really this turned into the square root of 2 plus 1 over x squared. So that's what I'm dealing with, is 2 plus 1 over x squared, because the square roots, obviously I could rewrite this as 2x squared divided by x squared plus 1 divided by x squared. So the x squareds cancel just as they normally would. So now it's pretty straightforward. Now I can find the limit. The limit of 3 is 3. The limit of 2 over x is 0. And the limit of 2 is 2. And the limit of 1 over x squared is 0. So I have 3 divided by radical 2. That's my limit, which if I'm going to write it as a horizontal asymptote, I would likely rationalize the denominator to get y is equal to 3 radical 2 over 2. So this is my horizontal asymptote. Now, as we do this for the negative side, we need to include something just a little bit different. So it's mostly going to be the same. It's still 3 divided by x, and I'm sorry, 3x divided by x minus 2 divided by x. And this denominator, 2x squared plus 1, is now going to be divided by the negative square root of x squared because we're approaching negative infinity. Oops, this is supposed to be negative infinity. And so this is really the only difference. So what difference is that going to make? Well, I'm still going to have the limit as x approaches negative infinity of 3 minus 2 divided by x. But inside here, I'm now going to have the negative square root of 2 plus 1 divided by x. So the only thing that's going to change is now I have negative radical 2, which means 3 radical 2 divided by 2, but negative. So I actually have two asymptotes here, plus and minus 3 radical 2 over 2. So again, that one's a little bit trickier because we're dealing with the square root inside of a rational. Let's take a look now at two trig function questions, and I apologize, we'll probably go a touch over 20 minutes in this video. In this first function, this is one that we've talked about before, and I said, hey, guess what? This limit is equal to 0. You'll use it all the time, just remember it. But we didn't talk about y. So let's talk about y. Sine of x oscillates between -1 and +1. So if you graphed sine of x, it would just go back and forth between -1 and +1. What if I divided everything by x? Still mathematically sound. What if I took the limit of everything now as x approaches infinity? -1 over x, the limit as x approaches infinity of sine of x over x, and the limit as x approaches infinity of 1 over x. Well, I know this limit is 0. I don't know the limit in the middle, which is why I'm doing this question. But I do know that this limit is 0, because that's what we've just been learning. And if this limit is between 0 and 0, by the squeeze theorem, the limit as x approaches infinity of sine of x over x is equal to 0. So the squeeze theorem just says, if you have a limit between two other limits, and those two other limits happen to be the same, the one in the middle has to be the same as well. Easy peasy. Let's do the same for the limit as x approaches infinity of x minus the cosine of x, all divided by x. So I'm thinking of this as x divided by x, or 1 minus, sorry, let's keep that limit in there as to not confuse anyone. The limit as x approaches infinity of x divided by x minus cosine of x divided by x, because obviously we can do that. Well, x divided by x is 1, but what is cosine divided by x? Well, we're going to do the same thing. -1 is less than or equal to cosine of x is less than or equal to 1. Take everything divided by x, and I get the limit as x approaches infinity of -1 over x is less than or equal to the limit as x approaches infinity of cosine of x divided by x is less than or equal to the limit as x approaches infinity of 1 over x, which both of those turn out to be 0, and therefore this limit is also 0. So what is my limit? 1 minus 0, or 1. Coming up next, we are essentially going to put together everything you've learned from 3.1 to 3.5 in a summary of curve sketching.